Hi everybody and welcome. The goal of today's video will be to identify, define, calculate, and solve functions that have symmetry, and also to identify those functions that are either even, odd, or none of the above. So a few definitions today, and we're going to jump into some of our actual real first calculations of this semester as well. So a bit of a balance today with some of the skills we've been doing so far. So first, to start off, taking a more visual look at things, reflectional symmetry. This is just saying a graph has reflectional symmetry if it can be folded over a line onto itself. So basically what this would be is if you could somehow center the graph in the middle of your paper and just fold your paper on top of itself, and if everything matches up perfectly, then you're going to see some reflectional symmetry. The second type of symmetry we're going to see is rotational symmetry. And this is a graph has rotational symmetry if it can be rotated less than 360 degrees and look the exact same. The reason why we specify 360 degrees is if you completely turn a paper all the way around, you're just back where you started. You didn't make anything new. So that's why there's no real benefit to rotating 360 degrees, because if we did that, everything would have rotational symmetry. It would always look the same if you did a full flip of it. So that's why we're looking basically at another part of that circle when we rotate things. Is it possible to get there? So looking at our example graphs below, for our first one, this is a really clear example of reflectional symmetry. So if we were to take our y-axis straight up and straight down, and we just folded it over that line of the y-axis, that would be reflectional symmetry, because everything on the left and right is an exact one-to-one match. The shape on the right is the same as the shape on the left. They're just basically flipped on top of each other. Now, the key thing with reflectional symmetry is it has to be able to be folded over a line. So this does not say it has to be able to be folded over the y-axis. It just says any line. So if you take a look at our second one, at first, when I saw this one, I was like, oh no, if I fold it over the y-axis, it doesn't fold onto itself, so obviously not. But the reason why I said a line so specifically there is, what if we use the x-axis as a line? What you're going to see here is actually, if you folded the paper instead of up and down, if you folded it side to side, this actually would rotate onto itself, and that would be another example of reflectional symmetry. So both 1 and 2 show us reflectional symmetry. And they show us in different ways. So this is reflectional symmetry on the y-axis. This is reflectional symmetry on the x-axis. And you can guess, yes, if it is, in fact, any line that it can be folded over onto itself, then you are going to see it not just on an axis, but on different points throughout. So speaking of those different points that we can fold things over onto themselves throughout, let's take a look at our fourth graph here. So I'm going to pause this here and ask us a question. Does this, number 4, where I put the star, does this have reflectional symmetry? And if so, the second question is, if it does have reflectional symmetry, where is it being folded over? What line is it being folded over on? So 2 parts here, true, false, reflectional symmetry. And then the second question is where, if it even has it. So I'll leave an option for that one. Maybe it doesn't even have it. All right, the second type that we're going to see here is rotational symmetry. And again, like I said, this is the idea that if you rotate something not fully 360 degrees, will it look exactly the same? So if we take an image of our graph down here and we move this exactly 180, so if we rotate this line exactly 180 on both sides, what you're going to see, not a full circle, but half of a circle, it does exactly match up with the other parts of itself. So this one here is an example of rotational symmetry. And like Bon Jovi, it's halfway there. 180 degrees. Okay, so not a full rotation, and that is why it does have rotational symmetry, because it's less than 360 and it will fold exactly over on itself at 180 degrees. Okay, so that's our first page here. Let's flip over to the back. So the first page, just looking at some graphs, some basic definitions. Page 2, this is where we get a little bit more interesting with our calculations. So even and odd functions, these are the two things that we're going to look at. And honestly, it isn't fair to say two things. Actually, really three things, because we can have an even function, we can have an odd function, or we can have neither. And oftentimes it is, in fact, neither. So key thing to note here, I know it's we usually think of these things like either or, it's either even or it's odd, but in this case it's even, odd, or none of the above. So taking a look at our first definition here, a function f of x, so f of x just means function, is considered even if for all x values, if we plug in the negative value of x, it gives us the original value of the function for f of x. So in general terms, what this is saying is if you plug in x and get back the original function, it's an even function. So an example of this would be, and I'll draw this right here, if we had the function, let's say, x squared plus 1. So what we could do is say, okay, if we do an x value of 2, that would mean that negative x would just be negative 2. So if we plug in both of these values, so f of 2, and we also plug in f of negative 2, for an even function, we would expect these to be the same. So if we did that, 2 squared plus 1, and negative 2 squared plus 1. So again, this is our x, and this is our negative x. If we plug both of these in and get the same thing, we're in luck. So 2 squared is 4, plus 1 is 5. Negative 2 squared is also 4 because the negatives cancel, and plus 1 is also 5. So this would be an example of an even function because x and negative x match exactly. On the flip side, we have something called an odd function if for all of our negative values of x, it doesn't equal the original function, it equals the negative version of the original function. So what this means in more general, less math fancy definition terms is if you plug in x and get back the opposite of the original function, it is odd. So another example of this, just to kind of demonstrate what we're talking about here, let's say we had something like f of x equals x cubed minus 8x. And let's do the same thing. We'll do 2 and negative 2. So if we had f of 2, and directly beside of it here, we'll do f of negative 2. We'll do 2 to the third minus 8 times 2. And over here, we'll do negative 2 to the third minus 8 times negative 2. The thing to be careful about with cubes is negatives don't cancel. There's 3 of them, so the negative actually stays. So negative 2 to the third power is negative 8, and then negative 8 times negative 2 is positive 16. So that gets us a final answer here of 8. For f of 2, if we have just 2 to the third power, that gets us 2, 4, 8. And then minus 8 times 2 is negative 16, which gets us negative 8. So we can see here is 8 and negative 8 are the same number with a different sign, and the reason that it's an odd function is because, yes, they are the same number, but there is a different sign. And that's the key to making the difference between even or odd. So that's the challenge for today, is determining is it even, is it odd, or if the numbers just don't match, no signs match, no numbers match, it's just all different, then your final answer actually would be none of the above, neither. So I'm going to take a moment and have you work through the first example, and then we'll check it together. So I'm going to put the star here for the video. Answer this question: is this even, odd, or neither? All right, hopefully you had a minute to pause the video there for a moment and take a look. Now let's see what it is. So I really like the number 2, so I'm going to keep going with 2. So we can plug in f of 2 and f of negative 2. What we can do here is 2 times 2 is 4 plus 4 gets us 8. And for negative 2 times negative 2 is again positive 4 plus 4 again gets us 8. These two numbers are the same, so we're going to go with even. All right, time to try number 2. So number 2, again, do the same thing. I'd recommend using the same number. I like 2. Why not? So go ahead, solve even, odd, or neither. Question number 2. All right, hopefully now that you've had a minute to calculate this one, we can go ahead and do the same thing that we've been doing. So f of 2 and f of negative 2. So 8 plus 2 plus 2, 2 to the third power plus 2 plus 2, okay. Double checking my math here, don't want to go too fast. So you get 12. And again, feel free to pause me if I'm going too quick. Take a moment to process, take all the time you need. Negative 2 to the third power this time is negative 8 minus 2 plus 2. So let's see, triple checking my work here. 2 times 2 is 4 times 2 is 8, that is negative. We have negative 2 and then plus 2. Okay, so we end up here with negative 10 plus 2 gets us negative 8. So in this case, 8 and 12 are not the same number. So this is an example of neither. So not even, not odd. We don't have matching numbers. Nothing we can do about that one. Move on with our lives. All right, last example time here. I'll start this one again. All right, hopefully now that you've had a moment to work through that one, we'll jump into even, odd, or neither, our favorite game of the day. So f of 2 and f of negative 2 here. So for our first one, 2 times 2 to the third power, which is 8, minus 6 times 2, which is 12. Work through this one, 16 minus 12 should get us an answer of 4. Next up here, 2 times negative 2 to the third power is negative 8, minus 6 times negative 2 is actually plus 12 this time. And then now, negative 16 plus 12 gets us an answer of negative 4. Hey, our numbers match. So 4 and negative 4 match, but their signs don't, which means we are looking at an odd function. All right, our last piece of notes here is a theorem that should help you with these things. So if a function is even, it will have symmetry with the y-axis. If a function is odd, it will have symmetry with the origin. So we're going to take a look at our examples from above, and we're going to see if this works. So the two that we're going to look at in Desmos right now, and feel free to pull up in Desmos on your computer, or if you have it on a phone or a graphing calculator to be even better. We're going to take a look at our first one, our even function, and then we're going to take a look at our second one, our odd function here. So those are the two that we're going to take a peek at in Desmos. So hopefully the iPad screen recording keeps working for us here as I pull open my new app. Very fancy. Desmos is free, by the way, as an app. So if you have an iPad or phone even, this will work for you if you don't have a graphing calculator at home. X squared, let's see, plus 4 is our first function. And what our theorem just told us is it said, okay, if we know that this one is an even function, so it should have symmetry with the y-axis. So I don't think I can highlight on this, but the y-axis is right in the middle of this. Obviously, this has symmetry. It folds over on itself right over the y-axis. So this looks like our theorem is an exact proof here. It works. So if we look at an image, we see y-axis symmetry. Without doing all those fancy calculations, we can say, bang, we got an even function. So let's jump to our third example here, the 2x cubed minus 6x. I'll punch that in, 2x. I'm going to test my knowledge here of, I'm not very proficient at Desmos, so see if I can figure out how to punch this into the third power. Let's see. Learning on the job here, no pressure, just a video that's going to be forever on YouTube for eternity. All right, so let's see, minus 6 times x. Okay, let's look at this guy. So what this is saying is that we have symmetry with the origin. So basically, if we look at the origin as our center point, and we reflect directly across the origin, everything should match up in like a straight line from it. So it's basically going directly through point to point from the origin. So if we look at our point at -1, we should be able to look at the exact opposite side of the graph for +1. So it's -1, 4. So if we look down at the graph, it should be 1, -4. And we see that these are exactly on the bottom here, and then on the top here, we see that those are exactly that. The same thing if we were to take a look at, I know it's a little bigger, 2. If we add +2, 4, we should see -2, -4, and in fact we do see that. So it's basically like you can draw from point to point a straight line through the origin, and it should bring you to the point for the negative value of that, which in this case it does for everything. So great way to take a look at these graphically. So 2 ways to solve today, 2 ways to show your skills. You can do it on a graph, and you can also do it by hand. I would definitely make sure you know how to do it both ways, because we're going to need to know how to do it both ways. So take a moment now, if you haven't already, get Desmos installed. You can also install it any way, shape, or form. You don't need to install it if you have a graphing calculator, though. But if you don't have a graphing calculator, again, a useful free app where you can do that. As always, thanks for watching. If you got questions, give me or Dennis a shout. We're here to help you. And let's get ready for those practice questions. Good luck.